Hello there. Today I want to talk about capability charts. These are the charts that you use to monitor production variance in manufacturing processes. We completed one of these charts in class, such as this one here, but today I want to walk you through the details of completing the chart so you can be successful in completing your assignments and any exam questions. Capability charts are very important for production engineers, where you want to monitor the mean and the standard deviation of a production process, so based on that you can estimate your design for manufacturability tolerances for the product. We'll now walk through the completion of a capability chart and you can see exactly how it should be done. So here we have our capability worksheet, and the first thing to do is to put all the information and all the data you have from the worksheet into the chart. But before you do that, the most important thing to do is complete why the data was collected, where it was collected, and when it was collected. So at the top, we will have location, which is University of Glasgow. We have the characteristic, in this case it's shaft diameter, and we also may or may not have a nominal specification. In this case we have a nominal specification which is 60.00 millimeters. If there's a part number or a reference number, you should complete the part number and a short part name or description. Here we'll call it a gearbox shaft, 60 millimeters, nominal, and the operation is final inspection. Now we can go ahead and complete the values into the chart here. There. That's all our data completed. Now you have to search through the data set and identify the maximum and minimum. I've done this beforehand. This is our max. And this is our min. You now have to decide on a scale to record the histograms along the vertical grid on the chart. So I've decided that my minimum scale will be from 59.86 until 59.87, and my maximum scale will be 59.96 and 59.95. So we'll write the scales into the capability work chart. Remember, the top of one histogram bin will be the same value as the bottom of the second histogram bin. So here we have 59.95 to 59.96. Here we have 59.94 until 59.95. I also find it useful to mark the interval with a small dash, 59.96 to 59.95, etc. And this makes it easier for completing the histogram figures later. After you've finished completing the bin widths for the histogram, just go over the numbers and make sure that you've not made some minor errors and copied the scales down wrong. After you completed the filling in and the completion of the data, you should find the min and the max, which I have done earlier, and then choose a scale, which you write in the first column of the grid on the capability worksheet. You then simply take each value in turn and record it as a histogram in the worksheet. So the first value is 99.934. So second value is into 59.901. 59.926. 59.912. And so forth until you complete the whole worksheet. When you have all the histogram completed and you completed the table here, you then need to transfer the top value of the histogram bins onto a scale on the left-hand side of the graph. So this starts here at 59.86 to 59.87. So we mark on the scale here 59.87. Once we have the scale along the vertical axis of the chart, we then want to plot the percentage against the percentage along the bottom line of the chart. You should notice on a capability chart, at the bottom scale, the percentages go from low percentage up to high percentage. At the top of the scale, they start at high percentage and go down to low percentage, with the mean being 50% in the middle of the graph. Plotting these, first one is 2%. We look along the bottom of the chart here to find 2%, move up and mark the chart. And we do the same until we've plotted all the points except the 100% point. The scale along the chart here only goes to 99.97. It can never reach 100%. So we discount the top value. So we have points for 2%, 16%, 50%, 84%, and 98%. And once we have that, we then plot our best case straight line through the chart. We have now completed the data plotting on our chart, and we can now read important values from the chart and fill in the rest of the sheet. First thing we can do is we can plot, and we can find out what the mean value of our plot is. The mean value is indicated at mu at the bottom of the chart. And our mean value in this instance here, 59.920. We can also find out from the chart what the spread of the results are. And in this instance here, it asks for the estimated capability across 8 sigma, which is plus and minus 4 sigma away from the mean. That's very easy to read. We have the 4 sigma lines shown on the chart, and in this case it goes from 59.88 up to 59.96, 0.08 millimeters. If we look at the top of the table, we can see two columns here marked upper specification limit and lower specification limit. We can write in these values based on the information we're provided with in the question. So in this case, our upper specification limit is 59.940 and our lower specification limit is 59.866 millimeters. And we can also transfer these results onto the chart. So 59.940, and I like to shade the side of the specification limits which are on the failure side of the manufacturing tolerance. In other words, product falling in this area above the line will fail. And the other one is 59.866. Now, using this information, we can see that our production spread is actually causing us to fail product above the upper specification limit at this point here. So looking on the percentage scale, we can see that 98% of our product is within specification, but we are failing 2% of our product above the upper specification limit. However, on the other end, we see that at 4 sigma point we are failing no product whatsoever, so the bottom is all within specification. Now we've plotted the chart, we can now calculate out the capability index and the CPK. So we have CP and CPK. First of all, the capability index CP is defined as the upper specification limit minus the lower specification limit divided by 6 sigma. If we take the upper and the lower specification limit, we get 0.074 divided by the 6 sigma figure. We can read that directly off the chart, and we can read minus 3 sigma here and the plus 3 sigma point here, which is 0.05, which is a CP of 1.48. We can also calculate the CPK, and the CPK index, you must take the nearest specification limit, subtract the mean from that, and divide that by the 3 sigma point. In this example here, we would take the upper specification limit because that is closer to the mean than the lower one. We would subtract the value of the mean, and then we divide by the 3 sigma value of the data. In this instance here, we would take this point here, 59.94, subtract the value of the mean, which is 59.920, which gives us a value of the 3 sigma point, which is 0.025, which gives us a CPK of 0.80. This is indicating that this process is controlled but non-centered. And looking at the graph, you can see that the mean value does not lie in the center between the two limits. It's offset to one side. The ideal location for this parameter here would be have a mean sitting somewhere in that node there, which would be 59.905, and that would be equidistant approximately between the two graphs. Last thing is to complete who performed the study, your name and signature, and most importantly the date on which when the study was performed. And there you have it. That's a complete capability worksheet recording the data in an easily understandable fashion onto the graph. Using this graph here, you can read off all the information and describe whether your manufacturing process is within tolerance or is outside tolerance. Of course, you don't always have to enter all the data into the chart yourself. You may actually be given a chart that has the data already plotted on the graph for you, and you're required to read the data and information from the chart and use that to derive control limits and customer limits for the production process. We'll look at another question where we're trying to address that problem. You can still proceed with this information here along with the information given in the question sheet. So here I've used the same data as the previous question, but I've only given you the upper specification limit, the lower specification limit, and the data plotted on the chart along with a scale. The procedure here is very similar to what you did in the previous question. First of all, you must pick the best straight line through the data set. So reading from the chart, you can read the mean directly from the chart. Which is the point it crosses, and reading across onto the y-axis, you can read the mean as 59.92 millimeters. Again, we can plot on the upper and lower specification limits, in this case 59.940, and again I like to cross-hatch on the failure side of the specification limit. And the lower specification is 59.866, so we have 59.87, 59.866 is here, and again cross-hatch on the lower side indicating where product would fail. We can calculate our CPs and CPKs in precisely the same method as we did previously. CP is defined as upper spec limit minus lower spec limit divided by 6 sigma. Upper spec limit is 59.940, lower spec limit is 59.866, and we can measure off the 6 sigma value from the graph from here and from here, and we know we get a CP figure of 1.48. Similarly, we can calculate out the CPK value, which is the closest specification limit. In this case, the one that's closest to the mean is the upper specification limit. So we take the upper specification limit, which is 59.940, subtract the mean that we have read off the graph, which is 59.92, and divide by 3 sigma, i.e. the point from mu to here, or the distance from there to there. And that gives us a figure of 0.80. We can complete the out of tolerance measurement. At this point here, which is at 98% point, we get 2% failures at the top level, and at the bottom we get no failures that we can see in the graph, so we say 0.0%. So only having the 5 points displayed on the graph, we can still derive the same information as we derived from the previous calculations. Thank you for watching this video. I hope you found it useful and informative on how you should use and complete capability charts for your manufacturing processes. Any problems, you can email me at the email at the end of the video. Thank you.